In this video, we're going to take a look at the 2013 free response questions 4 and question 6. Question 5 is an area volume problem, and I'm creating this for the year 2020, and we will not be doing testing area volume in 2020. So I'm just going to do questions 4 and question 6. So let's take a look at this problem. We have a graph. The figure above, it is to the right, shows the graph of f prime, the derivative of a twice differentiable function. We know that that's important. That tells us some stuff about continuity. On the closed interval from 0 to 8. The graph of f prime has horizontal tangents at x equal to 1. So there's a horizontal tangent. X equal to 3, horizontal tangent. X equal to 5, horizontal tangent. The areas of the regions between the graph of f prime and the x-axis are labeled in the figure, The function f prime is defined for all real numbers, and it satisfies the initial condition that when x is 8, y is 4. So there is an initial condition that we will probably use at some point within this problem. And they're telling us that the area of this region is 2. They're telling us the area of this region is 6. The area is 3, and the area is 7. So they've already calculated the areas for us. In letter A, find all values of x on the open interval for which f has a local minimum. So we know we're looking for the first derivative to change from, for a local minimum, negative to positive. And so, in this case, when we look at the graph, we see that the first derivative, remember this is f prime, changes from negative to positive only at x equal to, let me see what that number is, 1, 2, 3, 4, 5, at x equal to 6. So let's look at the scoring rubric and see what they say, because we do have to justify our answer. Sorry about that. So in letter A, x equal to 6 is the only critical point at which f prime of x changes sign specifically, and you can't just say changes sign, has to say change from negative to positive. Therefore, f has a local minimum at x equal to 6, and you get 1 point for your correct answer along with the justification. Okay, let's go back up to letter B. Sorry, my computer doesn't want to cooperate with me right now. So in letter B, we'll clear the board here. And in letter B, we are determining, now we're going from a local minimum to the absolute minimum. So now we've launched into the EVT, and we're going to have to consider the endpoint of 0 and the endpoint of 8, and we're going to have to consider all critical numbers. So if we go back and we look at the graph has critical numbers where the first derivative is 0 at x equal to 1, but there's no sign change there, so clearly it's neither a local max nor a local min at x equal to 1, so it can't be the absolute minimum. We have we have a local maximum at x equal to 4, so if you're a local maximum, you can't be the absolute minimum, even though you're a critical number, and I'm going to report it as a critical number. And then we have x equal to 6, where we said already there is a local minimum here, but that does not necessarily mean that that's going to be the absolute minimum. So to determine the absolute minimum, we're going to make a table of values, and we're going to accumulate area. So I'll show you the work in just a second. But in our table, we're going to include 0. We said 1 it can't be a candidate, even though there's a critical number. We said at 4 there's a local max, so it's not really a candidate for absolute minimum. We said 6 is a candidate and 8 is a candidate. So now we're going to accumulate the areas. Now remember, this is where that initial condition comes in. So we're going to, when x is 4, sorry, I have that backwards. When x is 8, y is 4. So we're going to start our area accumulation at 4, and then we're going to accumulate starting at the x value of 8 and stopping at the x value in question, which in this case is 0, under f prime of x dx. So what that looks like when I change colors here, we're accumulating the area beginning at 8, so 8 is right here, and we're accumulating to the left. So remember that all the signs of all of the areas are going to be opposite of what they normally are. So in other words, we have 7, so we have 4 units of area already accumulated, minus 7, This area below, because we're moving to the left, is now going to be counted positive, plus 3. Area to the left above is going to be counted negative, minus 6. And then the last area is minus 2. So we combine that, and that gives us our value for f of 0. All right, so if you look at the scoring rubric, you can see that they're doing the same thing. They are writing their integrals. They're accumulating the area. So f of 8 is negative 8. F of 6 is negative 3. And f of 0, was negative 8. And f of 8 is 4 because that's the initial condition. So even though there's a local minimum at x equal to 6, it's not the absolute minimum. The absolute minimum occurs at x equal to 8 and is negative 8. A lot of this is all about me sheet stuff. And then we're going to go to letter C. What open intervals contained from 0 to 8 is the graph of f, both concave down and increasing? Now remember, we have a first derivative graph, so let's think about first derivative and concavity. Wherever f prime decreases, f is concave down. Wherever f prime is positive, f increases. So we're looking for this graph. Let me clean it up a little bit, make my eraser a bit bigger here. Okay, so we're looking at the graph of f prime, and we're looking for two things. The first thing that I'm going to highlight is everywhere that f prime is decreasing, because that'll give me my intervals of concavity. So we have a decrease, we have a decrease. Okay, so those are our two decreasing intervals. Now the next thing we're looking for is where is f prime positive? Well, f prime is positive here, here, and here, and here. So we're looking for where they coincide. So our intervals are from 0 to 1 and from 3 to 4. Have I been reporting that number wrong? No, that's right. It's from 3 to 4. And that's not because of the 3, 4 here. This is a y value. I'm talking about from this x value of 3 to this y value of 4. So in letter C, as I said, f is concave down on the interval from 0 to 1 and from 3 to 4, and you have to state why. We want to justify with the first derivative because that's what they've given us, and we want to say the first derivative is decreasing and positive on these intervals. And then the last part of this question is just kind of a little baby chain rule question. So I'm going to clear the board again. And in this question, they are, where is letter D? There it is. In letter D, the function g, we have a new function, is defined to be f of x to the third power. And then they give us some information. They want the slope of the line tangent to g. So in other words, we need g prime of 3, which means we need g prime of x, which is going to require the chain rule because f of x is on the inside, 3 is on the outside. So when we perform the chain rule, we do the power rule for the 3. So 3, leave f of x alone to the second power, multiplied by the derivative of the inside, substitute 3, and then get your numbers. So when we go to the rubric down here, you will see the chain rule being applied. So you get 2 points for getting correct g prime. And then at this point right here, you can leave your answer as 3. Whoops, I almost missed that. So you can leave your answer as 3 times negative 5 half squared times 4. You do not need to get to the 75. All right, let's look at question number, as I said, question 5 is an area volume. And question 6, we can see right straight up, we have a differential equation in front of us. So let's walk through this one. We have the differential equation. It is a product. Notice that's e to the y multiplied by the quantity 3x squared minus 6x. So possible product rule coming in here if we have to go to the second derivative. Let y equal f of x be the particular solution versus general. Remember, general solution is plus c. Particular solution is when you solve for c. In letter A, we're going to write the equation of the line tangent to the graph at f at 1, 0, and then we're going to use that tangent line to approximate of y value. So anytime we write the equation of a line, we begin with the point slope form of that line, and notice that they've already done basically 2/3 of the equation by giving us the point 1, 0. So we know we're going to have y minus 0 is equal to, I don't know the slope yet, x minus 1. So now I'm going to need to compute the slope by using my slope generator of dy dx. I'm substituting 0 in for y, and I'm substituting 1 in for x. So if I substitute 1 here and 1 here, that'll give me 3 minus 6, which is negative 3. E to the 0 is 1, and 1 times negative 3 is negative 3. And I can distribute that, but I do not have to distribute that. And you can see, whoops, stray mark, you can see the equation of the line right here. Now, when we find the approximate f of 1.2, we're simply going to substitute 1.2 in place of x, and we're not going to simplify that. We're not going to distribute. We're not going to subtract. We're going to multiply. We're going to leave our answer just like that for a full credit answer. And then finally, this question only has a part B. So for part, let me turn the page and see if I have it in 2 sections. Nope, there's only a part B. So in part B, we are solving the differential equation. So when we solve the differential equation, there are 3 steps: separate, integrate, solve, solve. So when I separate, I'm going to get the y terms on one side. I'm going to divide both sides by e to the y. I'm going to get the dx on the right-hand side. So I have 3x squared minus 6x. This is not a bad one at all. Dx. Now, the only thing that I would be concerned about, anybody struggling, is how am I going to anti-differentiate dy over e to the y? We're going to take that e to the y and move it to the numerator, make it e to the negative y. dy equal to, the right-hand side, of course, is easy to find the antiderivative of, so I'm not really going to focus so much on that. So over here where we have e to the y, we're going to take it to a u sub, and we're going to let u equal to negative y. Therefore, du is equal to negative dy. And we don't need that negative, so we're going to move it. We have to compensate for that. So that's negative du equal to dy. And if we carry forth the u substitution, we would have negative integral of e to the u du. And the antiderivative of e to the u is simply e to the u. There's my negative being brought over. So when I come back up to my work up here in blue, I will have negative e to the y. And on the right-hand side, I'll have 3x cubed over 3 minus 6x squared over 2, which is 3x squared, plus c. All right, now in this problem, I'm trying to decide what I'm going to do. I think I'm going to solve for c now. You have to make that decision. Sometimes it's easier to solve for y. Sometimes it's easier to solve for c. I think in this problem, it's easier to solve for c. So I'm going to use my initial condition of 1, 0. So I have negative e to the 0. Substituting 1 here and 1 here, I'll have 1 minus 3, which is negative 2, plus 3. And e to the 0 is 1, so I have negative 1 equal to negative 2 plus c. Add 2 to both sides, and c is equal to 1. So I'm going to come back where I left off, which is negative e to the y, x cubed minus 3x squared plus 1. And to get y by itself, first I'm going to divide both sides by a negative, and that'll give me negative x cubed plus 3x squared minus 1. And then finally, to get y by itself, I'm going to take the ln of both sides. So if I take the ln of e to the y equal to ln of, and it's not absolute value, negative x cubed plus 3x squared minus 1. E and ln are inverse operations, so they do undo each other. And I have y equal to ln of negative x cubed plus 3x squared minus 1. And you do not have to state the domain to get these points. Negative x cubed plus 3x squared minus 1. Let's see, they have negative. Why do I? Oh, I know why. You know why. Oh, I think you know why. Why? I don't know why. Oh, I see. You probably already picked up on it. Back here when I did my u substitution, when I replaced u, I didn't put the negative y in there. Oh, so that's gonna mess up my work. So anyway, what it does is it gives me a negative in front of ln. So I apologize for that mistake, and I'm happy that you caught that mistake right back here when I forgot to substitute negative y there. So that would just bring a negative y back into my work, and that would give me the same answer that they got if I had that negative in there. So let's see what it would have cost me. I would have gotten my point. I separated the variables correctly. I had both now the antiderivative may be where I lost the point. This point possibly is separated, 1 point for one side and 1 on the other. Somewhere it's going to cost me, probably here in the antiderivative point. Maybe I'll get 1 of these points instead of 2. I'm going to get my constant of integration point, my initial condition point. The reason that they're going to keep reading with me, probably in this case, is that my mistake didn't really make the work that much easier. It didn't significantly change the problem. So what it's probably going to cost me is either a copy error or the antiderivative, but I think probably it might cost me the y as well because I don't have the correct answer. So I think I would have at least 4 points out of 6. So that's not bad. I'll take that. Hope this helps.